All right, welcome to the fifth and final part of chapter 18. We're going to do just one reaction from the last section. We've been talking about electrophilic aromatic substitution, and so we're going to wind this down with a nucleophilic aromatic substitution reaction. There are a couple different reactions here at the end, but we're just gonna look at this first one. These are a little bit tougher because we're trying to attack a big cloud of electrons with a nucleophile, which isn't usually something you would see. And so it requires that we have a couple of things already on the ring. We need to have a good leaving group like our bromine. Chlorine would work here just as well. And then we need to have a really strong deactivating group. We need a nitro, and it needs to be in a certain position. So we're gonna talk about that in a minute, but it's important that it's in the para position right now. This is a two-step reaction. It's going to use sodium hydroxide and some heat, and then you're going to do an acid workup, a little H3O plus. That's going to make sure that at the end your alcohol is protonated. Phenols tend to be a little bit more acidic because of the resonance. And so if you leave it in that sodium hydroxide, it will deprotonate. Okay, so let's look at this and start on the mechanism. So it's up over here. The mechanism is following. Oh, okay. We'll make the note now, so that I'm following the slides. This nucleophilic aromatic substitution, right? These two things are really important. You've got to have a good leaving group, and you've got to have that leaving group ortho or para to your electron withdrawing group. So the nitro could be here, or it could be here. You need that ortho or para pattern for this to work. If the nitro is meta to the bromine, no reaction will occur. So let's look at the mechanism to see if we can understand. We're not going to make a sigma complex, but we are going to make something called a Meisenheimer complex. So we're going to start off with our nucleophilic attack. We've got that electron density being pulled away by that nitro group. We have our good leaving group. You can do bromine, you can do chlorine. It doesn't matter. You're using sodium hydroxide, and so you are going to attack that position. Now, it's not an SN2. You can't do SN2 on an sp2 carbon. So the leaving group is not going to leave in this step, but you are going to create a carbanion. And this is where we get into our resonance. So from here, you're going to have a negative charge on one of your carbons. You're going to have your leaving group and your OH, and then you're going to have your NO2. And you're going to have several resonance structures. All right, so bear with me while we write these out. If these move down, and it'll push that pi to the bottom carbon. And then we will have a negatively charged carbon. Now I'm going to draw out the NO2 here so you can see why that ortho-para positioning is necessary. Because in the ortho and para position, that negative charge is going to wind up on the carbon with the nitro. That's going to give us an additional resonance structure. And if it was in the meta position, you wouldn't have that additional resonance structure. And hopefully by now we're starting to realize that the stability of these intermediates comes from the stability and number of the resonance structures. All right, and then there would be one more. Trying to draw this small enough so I don't mess it up. BROH. I'm just going to go back to abbreviating my NO2. So if the nitro is ortho or para to the leaving group, you are able to get all 4 structures of the Meisenheimer complex, stabilizing it enough for this reaction to occur. Now, from here, we want to show loss of leaving group. They used this structure, and you notice you need to make 4 arrows because you need to regain aromaticity and you have to show that electron flow. I'm just going to go from this one. It's a little bit easier. I'm going to show that lone pair falling in and kicking the bromine out. It doesn't matter which Meisenheimer structure you use. You just need to pay attention to what your arrows are saying. And that is going to reform our aromatic compound. It doesn't matter if I draw the opposite Kekulé structure, right? We know benzene rings are in resonance, or have resonance in O2. Now, you don't see the second step with the H3O plus, and that's okay. Most of the time when I draw this mechanism, I made the product and I stop. But you have to remember you still have OH around, and that can deprotonate that phenol. So adding in the H3O plus just ensures that you have your protonated alcohol. All right, this does not work if there is no nitro group most of the time, but you can force it, right? 350 degrees C, pretty high temperature. You may have to think about the logistics of that reaction. And so you're not going to see that reaction from me. I'm going to make sure that we have our nitro group. Oh, I'm sorry, this was getting into the next step anyway, talking about elimination addition. We're stopping at nucleophilic aromatic substitution. So you can stop at section 13. That is as much as I'm going to test you over. And that's all of chapter 18. I will see you next week in chapter 19.